member of this Diploma of Physics, Hong Kong U. I'm going to chair this session. Today, the first speaker, we're very glad to have Dr. Shiuh-Wuu Lee from SMIC. Dr. Lee joined the SMIC 3 years ago. Before that, he was at Intel, AT&T, and Bell Labs. Dr. Lee has over 30 years experience in the semiconductor industry. So 3 years ago, he moved to China. So today, he's going to talk about the China's IT industry and the strategy in of SMIC. Let's welcome.
Good morning. I'm Shiuh-Wuu from SMIC. I manage the entire technology R&D at SMIC. And first of all, I want to thank the organizing committee for inviting me to this excellent conference. And I read the agenda, and it was really a lot of nice talk. And unfortunately, been pulled by many meetings and other day-to-day mundane affairs at the company. I couldn't come the last 2 days, but I'm sure once I have the slide, I will pull through and learn a lot about the newest device physics, modeling, and other areas. So today, I prepared a talk. It's relatively short. As I was telling Philip, my secretary misread it, and he thought I have 30 minutes. Okay? So it turned out that I have 1.5 hours. But I probably give somewhere in between. And I'll open up for questions at the end of my talk. And I will slow down my talk here a little bit. Okay? I usually talk very fast. So the title of my talk today is China's IC Industry and the Strategies of SMIC. We have so many world experts on device physics, processing, modeling. So I think it's probably somewhat useful for me to approach this my talk with a slightly from different angle. So I will talk about IC, China's IC industry, briefly. And also SMIC is a small foundry compared to TSMC, or even Global Foundry, or even UNC. How do we plan to survive in this competitive industry? And not only survive, hopefully we can flourish. And what are our strategies? Oh, okay. Safe harbor statement, as usual. Now, this is the outline of my talk. First, I will cover from several different angles about what's happening in China, in China's IC industry. Then I will talk about, by looking at some of the data, you probably will agree with me that the China IC industry is expanding, probably the fastest in the world. And that brings to SMIC both opportunities as well as some very enormous challenges. And finally, I end my talk to describe some of the strategy that we put in place. This slide shows the worldwide IC market share by areas. And we look at 2000 and jump by about 6 years. Okay? In the year of 2000, well, we look at this pie chart. We look at what is the share of US or North American market, which was 66 billion. Japan was about 48 billion. Others, 94 billion. Europe, Taiwan, South Africa, South America, etc., etc. China market share was about 15, which represented a 7% of the worldwide market. In 6 years, the same pie chart, but the number changes, the distribution changed. And you can see China went up to from 15 to 68 billion, jumping from 7% to 26% of the total world IC market, IC industry. Another 6 years, China went to 107 billion. Again, that's going from 26 to 33%. And we are projecting in 2017 that will reach around 137 billion. So another increase to almost 40% of the worldwide market. And this chart is looking at the revenue of IC design houses. I do have a slide which is showing the entire IC ecosystem. It has foundries, has fabless design houses, has tool makers, EDAs, etc., etc. So this by no means is the only aspect of importance in terms of China IC industry, but it is a very important. Is the fabless design houses, their revenue. And we're looking at from 2011 all the way starting projection on 2013, we're not quite at the end of it yet, by about a week and a half, and into 14, 15, and 16. You can see that on the blue bar represent the global. Okay? That's also in terms of US billion-dollar unit. And you can see that this is in the orange color is the China IC design houses. And the compounded annual growth rate of the overall worldwide design houses is increased by around 5%. And yet China is over double digit, about 11%. I should also mention on this chart, when did the China design houses start? It's about 1990. It took China, for some reason, it took China, the design industry, had a very slow start. It took them about 8 or 10 years to reach a revenue of about $1 billion, which is around probably 2000 or 2001. And then at that point, the design industry in China took off exponentially. After they reached that point, it just grows. And then, of course, you cannot continue to grow at the same rate, but still at a very respectable rate of about 11% since 2011. So that's another aspect. Now, looking at the same data or same issue, same aspect, and this is about the industry's revenue from 2007 to 2010. Just looking at its revenue in blue bar, and the black plot is the annual growth rate. You can see that roughly it's over 10%. Okay, that's what we're showing the average. It's compound annual growth rate of about 11%. And this is breaking down by year to year. Okay, what are the driving force behind the China IC industry's tremendous growth? And we can look at those categories. The industrial electronics, okay, and we're looking from 2012 through 2016. So there are some solid data, and there are some projections, okay. And so things can change. Okay, so there are some projections here. So industrial electronics and the compound annual growth rate through those 5 years and is about over 15%. So that's a strong segment. Automotive electronics, also a very strong segment. It's about 13% compound annual growth rate. Wireless communication is about 8.2, Data processing about 5.5, wire communication about 4.5. And you also have consumer electronics about 3%. And looking at 2013, the tablet and smartphone are the hottest product on the China market. In addition, there are additional applications emerging and will come in a big way. Is IGBT, MEMS, MCU, and smart card. And as you will see later on in our strategy, in the technology strategy at SMIC, there are multiple reasons behind our strategy, and I don't want to jump the gun. I will go into that in a little bit of detail. But here I just want to say that you will also notice later that our focus in our value-added technologies are addressing some of the strong growth areas, particularly in China. For example, the MEMS. For example, smart card. As some of you are already very much aware, in China it started in 2013 in a little bit smaller way, but certainly in a bigger way, 2014, 2015. There's a big push that all citizens will be carrying smart card to their banking and so on and so forth. So that will be a significant market, and SMIC is well positioned to address that market. In fact, many of the institutions already start adopting our technology.
Will you count that as consumer electronics, or where does that fit in this?
That would be consumer electronics. Okay. China, has tremendous export, but also on the importing side, which is the biggest importing segment. People might guess oil. Right? This is a manufacturing center of the world. You must be burning out a lot of oil, which is true. We import a lot of cars, including high-end luxury cars, right? You see the Shanghai automobile shows, right? People just buy the cash on the spot, right? You heard a lot of stories. Well, yes, those are big imports to China. But the biggest one is semiconductor, IC supply. That's the biggest single import to China. Bigger than oil, far bigger than car. Okay. And if you look at the data, starting from 2000 and, my eyesight is not very good, sorry, 2007, and projecting all the way to 2017, and there's always a gap. This is the demand. This is the supply. And the gap is, roughly speaking, is an import. Okay? And you can see that while the China's foundry industry is growing, like SMIC was founded around 2000, right? So we do supply some of the internal demand, and we are growing. But however, the supply, the demand is growing faster, and it is anticipated by 2017 the gap will be around $40 billion. Okay. So this is a challenge to the Chinese government, and this is also opportunity for companies like SMIC. But opportunity to seize that opportunity is not easy, okay? But it is an opportunity. All right, this I will get into the second part of my talk, which is the rapid growth that brings opportunities and challenge to SMIC. Well, this chart shows the number of design houses, domestic design houses in China. As you can see, around 1992, the whole industry started around probably 1991, 1990. So it was a slow growth for about, as I said, about 10 years, roughly, 8 or 9 years. And then suddenly, around 2000 and 2001, there was an explosion. And now we are reached over 500. It has a little bit saturation, but it still continues to grow. And this is a tremendous opportunity for SMIC, but also a challenge. Let me explain. Of course, the opportunity is self-evident. They need to manufacture their product. And many of the products are on the technology node that we can provide. 0.18, 0.35, 0.13, 0.11, or even 65 and 55. And now they're getting to 40 nanometers. But of course, on another later chart, I will show you that some of the companies are pushing very hard on the most advanced technology, and that is a challenge. Because those products are also of the highest ASP. Okay? So while the number of companies increase, it gives us the basis to have a more or less stable and growing revenue source. But on the other hand, there's other challenge. The China's domestic design houses are maturing very fast. Okay, and I have all the respect and wish them all the best, best wishes to them. But on the other hand, many of these, especially the smaller ones, they are not very experienced design houses. They need a lot of handholding. It's not like the USA Broadcom, Qualcomm. They know what they are doing. Okay? They have a very well-defined procedure, how to qualify their process, sponges process for their product, etc., etc. In fact, a lot of their input actually help us to make our process even better before we engage with them. But with the China's domestic design houses, it's the other way. So we found out, for example, at the beginning, we focus on technology available through foundry service. Then we found out it's insufficient. We don't have the IP. Okay. When they do design, you want to do design easily, faster, lower cost. You need IP. Okay. We didn't have that. So that was one of the weaknesses we discovered maybe around 2010, 2009, 2010. So we spend a lot of money every year to implement IPs, starting with 65. Probably not 90. 90 was a minor node. 65, 55, 40, now 28. We invest tremendously. That's just one example. Okay. That we need to work with them. So not just the technology, but design service as well. Customer engineering needs to get into the picture to help them. To provide information and so on. So it's both an opportunity as well as a challenge. Okay? And I just mentioned a couple of the challenges. Our IP, and also they need a lot of on-site consultation, how to utilize our PDKs, SPICE models, design rules, DRCs, etc., you name it. DFM, all the complete portfolio, what I call design enablement, technology-based design enablement. So we're putting a lot of emphasis into that. Okay, remember a minute ago I was saying that yes, we still have a lot of revenue on the mature technology because a lot of Chinese design houses, their product, their design is still based on some more mature technology. But this chart shows another aspect. The green represent, and this is a timeline, 2005, 2010, 2015. So every 5 years, okay? And the green dot represent at about 2001, what is the available technology that SMIC can provide. This is in about 2001, 0.35. About 2003, 0.18, about 2004, 0.13, etc. 90 nanometer about 2007, and 65 around 2004, 2005, and then we since 2012, the 40 nanometer low leakage technology is fully into volume manufacturing. And by the way, I will talk a little bit more about it. The 28 nanometer And for you may be interested, I know Mark Stadler, my old colleague, and he said, "Wow, we have done that before." Okay, yes, yeah, Intel is leading. Okay, but we depend on ourselves mostly, and in fact, we will be finish up 28 nanometer at the end of the year, and I'll tell you a little bit more detail. There's a lot of excitement there. But what is the demand from China's domestic design houses? Well, back in 2001, we have 0.3. I reversed. Sorry, the blue one are what can be provided by SMIC. The green one is what's required from the domestic design houses. Sorry, I reversed that. So in 2001, we could provide 0.18, but the China's design houses, on the average, they only want to use 0.35. So we are one generation maybe ahead. And then still goes around about 2002. And then when you reach about 90 nanometer, they start to hit about the same time. In other words, we can provide 90 nanometer actually slightly behind what our leading domestic houses wanted. They wanted a little bit earlier, but our process wasn't ready. Not much, not by much, but by maybe a year. Then the picture changes. When we hit 40 nanometer, what they want is a little bit early, even earlier than 90 nanometer, what they wanted. Now, I'm not talking about the average so-so design houses in China. I'm talking about the China's leading, the big design houses. Now, if you look at 28, the gap is even bigger. It's about 2.5 years. Okay. So that doesn't mean we don't have opportunity to capture business with them. Okay. There are many ways to capture business, but this is a fundamental problem. We need to narrow the gap while the ASP and the demand is very high. Okay? So that's one of the challenges. Yes. Oh yeah. By the way, feel to ask questions along the way because I have plenty of time. Go ahead. Philip.
What is the demand behind this push to 20 nanometers? Is it telecommunication products or MCU?
Not MCU. It's like some AP application processor. Both used for and also for their smartphone processor. Mostly like that. Our CPU, real hardcore server CPU, we're not into that competition. We leave that to Intel, AMD's, and maybe some of the other processor companies like Qualcomm and so on. They are competing for that. Yes.
The design houses, right now, they make up that gap simply by importing a chip.
Oh, no. Right now, for example, I don't want to name names, okay, that's I'm restricted from doing that. But some of the leading Chinese domestic design houses, they go to TSMC. Okay. I will talk a little bit more about 20. I think this is a very, very important technology for everyone, for design houses, for SMIC. Yes, to answer your question, right now they go to TSMC, depending on which flavor of 28 nanometer, some may go to global. Okay, but if you talk about real high performance, high K metal gate, and gate last, right now is really TSMC is the sole, or practically the sole provider, with good yield. I heard there's some progress also being made at the UMC recently. Okay, but they had some period of trying to improve their yield. But they may have got over the hump, but I'm not 100% sure.
So the Taiwanese, just to get perspective, you said 570 design houses
in China. Uh-huh.
How many are there in Taiwan?
Oh, that I don't know how many are in Taiwan, but the leading I don't want to name it, but the leading design houses, when they need 28, there are several of them. They go to TSMC. But when our technology become available, such as the experience on 40 nanometer, many of them will also start coming back. Not abandon TSMC. I don't want to give you that impression. You know, as any business, you don't want to have a sole supply. That's a very dangerous thing to have. Okay? And this goes not only with domestic design houses, even with leading U.S. factories, extremely large companies. They don't want to depend on one company. Even though TSMC may treat them like a kid or queen. I know there's some ladies here. But this is not good practice. Internally, you know, we look at the OPC, we look at other things. I don't want my team to rely on one vendor for the same reason. Okay?
One last question. So you also projected the growth of smart cars and MEMS.
Yeah.
And they tend to be on older technology nodes.
Yes.
But it doesn't seem like that's driving the design house demand. Because this is more from the application process, the computing side standpoint.
Yeah.
So why
Let me give you another data. I don't have a good graph to show what is the growth potential. I will project the one internal projection on MEMS, CIS, and so on. But I know also PIM, power management IC. It's a tremendous business. But I give you one number, overall number. The total revenue, out of the SMIC's total revenue, I would say about 55% to 60% are related to logic, are based on logic technology. Various logic technology. I do have a chart. Okay, it's not just AP, application process, there are many others. But based on logic technology, it's about 60 to 65%. MEMS, IPD, integrated passive device, high quality, high Q, extremely high Q inductors, CIS. By the way, SMIC is the second largest CIS provider in the world. Okay, we are already very big, but the potential of growing is tremendous. I don't have the number with me. I don't have a slide. But I can tell you our internal project, I just have a small factory built or started. It's relatively small. It's dedicated to, which I will talk about a little bit, MEMS, sensors, CIS, which means CMOS compatible image sensor, 3D IC, interposal, those kind of technology is going to be a very high potential growth area. So the specialty technology, there's also embedded on model memory, etc., etc. That's already 35% of our revenue. It's not irrelevant. But then, which one do you put in more resource? I think you will see a little bit, I can give you a little bit of flavor how we leverage the logic. Okay?
You just said earlier, there's China import a lot of electronic device.
A lot of IC,
IC, yes.
Electronics, yes.
It's more than even oil.
Yes.
So I wonder what's the main reason? Is it because of hardware, or it's also because of design house?
The internal, the China's foundry internal, it just, I think we made a good progress. If you look at SMIC, we are the leading foundry. Okay, so you can see that we are growing, we have been growing, especially since the new management team came in at the end of 2011. We had, for the first time in the company history, we have 6 or 7 quarters in succession of profitable quarters. And our revenue will be around $2 billion. Okay. However, if you look at what's the demand, it's just so big. So big.
So I'm wondering why there's a gap. Here you show because of the hardware.
Hardware?
Hardware because, for instance, here shows design house around 28 nanometer.
Yeah, you mean the technology.
Technology.
Yeah.
So it's because of the hardware technology is behind the demand. It's not the software and design.
I cannot say not because of design, because there are a lot of product imported into China was completely designed and manufactured outside of China.
As well.
as well. But there are also probably Chinese design houses went outside for manufacturing and then importing it. So there are different cases. It's all combination of those. Okay, I don't have a fine breakdown on that. But anyway, the final observation is that yes, indeed, the IC electronic is the single largest importing domain. Okay. Okay, so we are watching this very clearly. I don't have the chart here, but also I should say that among the foundry, another way of looking is that how much of SMIC or all the foundries, TSMC, UMC, and Global, and so on. Another way of looking at it is how many percent of each of the company's revenue is coming from the advanced node. Okay. For example, as I said, 28, let's say high-k metal gate, TSMC is already making tremendous amount of revenue out of it, for about 30-some% or close to 30%. Very significant. All the rest of it is beginning. Okay. And we haven't even started yet, but we will very quickly, okay, which is a good news. But on the 40 nanometer, that is still a very large revenue generator for the foundry industry. And we are very close to UMC. Only slightly below. If you look at, that's one way of looking at it. I'm not saying that's the only metric. But one metric is that how much of your company's revenue coming from 40 nanometer? What is the percent of your revenue coming from 28 or 65 or 90? You know, and is our percentage of revenue coming from the 40 as good as much as, say, some of the other foundry? So we are making some ground, and I think that we are very close to UMC, slightly behind, but TSMC, of course, is way ahead. Okay. All right. So that's a challenge. Okay. SMIC needs to provide advanced technology sooner, and so on. Okay. Now, this is one way to look at SMIC's revenue coming from China's money. Okay. And this is something we didn't see before, I haven't shown before, but this is a SMIC revenue coming from Chinese money. 2007, only 10%. 09, 20. 12, 34. Now we are close to 40. Okay. And by end of 2013, we should reach about 40%. So we are also, not only we are working with the Broadcoms, the Qualcomms, and all sorts of international companies from the US and Europe even. Okay, they are all growing. But the single biggest growth is in China. And this is one of the intrinsic advantages of SMIC compared to other foundries. And we have to seize upon opportunity. If we don't, we cannot blame anybody else but ourselves. Okay? But we are doing some growth in China. This is among our revenue. But we need to capture bigger. If our pie is very small, so you get 100%, so what, right? You need a total pie to increase. So that's another, it's not displaced here. So that's something we hope to achieve. Okay. Just briefly, I think that touches upon probably your question a little bit. Is that why is is it just because we don't have technology? Well, the answer is yes. TSMC already has 28 high-k metal gate, and also LP. And in fact, they have LP plus. What about SMIC? Well, LP is coming out, high-k metal gate is coming out by end of December, okay? And which is 2 weeks from now. Yesterday, I was in a company-wide quarterly communication. I had a thorough report to the company, or the employee actually, how well, what is our status of 28 high-k polysilicon. And so far we're doing very well. We only have about a week and a half before my expected due date to my team, and I think we're hit it. Okay? But that's still, we're behind, right? So that's one reason. The other reason is capacity. Okay? And many of you know as well as I do, how expensive it is to build a 12-inch fab. It's not a trivial task. If you overbuild it, you'll be in trouble. If you underbuild it, you'll be in trouble. you lose business opportunities. So what is a sweet spot? While the industry going through every 2.5 years, there's a cycle. Now, with Mark's company, my ex-company, they have a lot of money. Probably not a big issue. But I know, Mark is no problem. But SMIC, we need to be very careful because, as I said, even though we achieved 6 quarters of profitability, which never happened before in our company's history, but however, our profit is minuscule compared to some of you guys' company. Okay, so we have to be very careful. That's a challenge. But still, we are doing expansions. I should mention that in Shanghai, we have an 8-inch S1, we call it S1 MegaFab. It has 94K, 94,000 wafer per month capacity. It adjusts from 0.35 to 0.11, has both aluminum as well as copper backend. Now, you say, wow, that's all old technology. But later on, I will show, and I think one of the questions is that we are actually leveraging those ones. For example, very interesting CIS technology, like 0.11. We're implementing what we call BSI, backside illumination. And that will get into full production in Q1. Okay? So that will supply the higher end, I wouldn't say the highest end, but higher end CIS market for cameras and things, product like that. Okay? So this is a very profitable fab and a good size. But also in Shanghai, we have a 12-inch smaller fab called Fab A. It's about 1.5K, 15,000 wafer. It's going to address 45, 40, as well as a little bit of 28. A little bit of 28 is because we developed, my team, most of the TD, about 700 people, are located in Shanghai. I do have about maybe 80 people in Beijing, okay? But that's a little bit much smaller. So most of them are in Shanghai, and we utilize both S1 on the 8-inch technology, like CIS, MEMS, those kind of TSV, those kind of things. But for 12-inch, we develop our 28 now. In fact, we started 2014 FinFab, also in Fab A. So this fab is small, but it's half of it is for R&D, support R&D. But the other half of its mission is to manufacture. So it has relatively, but because we develop in Shanghai, we can support a smaller demand from the customer immediately. Otherwise, we have to wait for transfer from Shanghai to Beijing. And then you need to go through a thorough qualification. Some of you know how much time and how complex that qualification is. Maybe even for digital product process, but if you get into RF process, it's almost a nightmare if you want to transfer. Okay? So anyway, so Beijing, we have already a B1, which is about 36,000 wafer per month. It addresses 0.15 all the way to 65 and down to 55 nanometer. But coming up is B2. It will be a brand new fab. It will be, the first phase will be 35,000 wafer, and the second phase we haven't started yet. First phase is under construction. All the buildings are done. The rooftop closed. All the tools will come in by March. And the fab team, B2 team, was already in Shanghai to start working with my team side by side to learn the process. So by the time we freeze another quarter, maybe 2 quarters of qualification, then they take directly into Beijing and maybe start doing some risk production around June next year. Okay, so this will be about 35,000 additional capacity for 28 and also for 40. And then if we need it, there will be another phase B3, will be another 35,000 K. Okay, that's our plan. We also have a Tianjin for some earlier, like high voltage, discrete device, etc., etc. And also we are building a fab in Shenzhen, down south of China. And the building is already there. We never put in tools, but now we are putting tools. And we hope to bring that up, and that will be for specialty process, such as RF, SOI. And that's also a big part.
There's no MEMS anywhere.
Oh, there'll be MEMS, yeah. There'll be MEMS here, there'll be also MEMS here. Yeah. Okay?
So could you comment on the fact that you're choosing the 8-inch platform that you...
Why choose the 8-inch platform?
Yeah, well,
Yeah. When we do a technology, when we have a market, we will look at what is the cost, the final cost to the customer, and also what is the profit margin. Some of the reason for 8-inch is because all the depreciation are worn out. I mean, it's zero depreciation. That's a big chunk of the money. Okay? And some of the toughest when you go to advanced technology is that once you have the tool in, you have to depreciate completely in 7 years. And you know the tools. And some of the tools are $10 million per tool. And you have many of those tools. And that's a tremendous thing. But of course, for advanced technology, logic product, we do need that. And we are buying tools. Okay? But whenever possible, we also consider 8-inch. But, sometimes we are doing two. Later you'll see my CIS roadmap, okay, like BSI, which is sort of new technology, backside illumination. We first implement on 8-inch. But by looking at the demand and our customers' roadmap, we were also doing on a higher technology, or newer technology, like 65 nanometer, 12-inch. So we're always considering the cost and what's needed to drive the required performance.
It's also there's no 3.5s anywhere.
No. Yes, I think that's an interesting comment. I mentioned that we are getting into SOI. Okay, we have never done it, but we are getting into it in a big way.
Will that be
However, at this point, we're not doing pure 3.5 devices. But on the other hand, when you get into 10 nanometer, okay, even your CMOS channel, you need some different materials. In that respect, we have to understand some of the different elements and put into the pure silicon material. But those like gallium arsenide, HAMD, those kind of devices, we're not looking.
Are there Chinese companies in that market?
Yes, there are some. Yeah. The details I don't know.
Okay.
The details. But we are looking at the market size. We are looking at our key customer. What are their roadmap? And the customer, I should say, not just China. We're working with U.S. companies, big U.S. companies, like the SOI, RF, and so on. So we're looking at those as well. Okay? All right. The ecosystem. As you know, there are many components. Foundry being one of the most important one. Mask making. IP provider, we talk about how important IP, especially to some of the smaller companies, less experienced design houses. Fabless, they might need IP, they might not. Even to design service, as I said, some of the less experienced design houses, we work with them closely, hand in hand. And not just the wafer level, but also package assembly, bumping, and CPU testing. But also, you notice that this too is that in China there is a concerted effort trying to look at the overall infrastructure. What are the key components, and which I just mentioned, but including hardware and material, some of the chemical suppliers, some of the new materials, some of the tools, etchers, you name PVD, and all sorts of thin film tools, implanters, and so on. And our role in this is that we are focusing on the blue box, right? This is what SMIC provides directly to our design houses. But we are also working with packaging houses, but we are also helping to drive material and hardware industry. Now, I shouldn't say drive. We are working with them. They bring their tools into our company for qualification. And since we are the leading foundry, we have most of the time, probably not 100% of the time, but most of the time we know what is required. And we look at that, we will feedback, say, no, this aspect is no good, that is not qualified, why, and so on. And we give them data, sometimes we will give them our own analysis to help them. So I can tell you just roughly, On the 65 nanometer, we have a very significant amount of the materials and tools are domestic already. 40 nanometer, we have a little bit lower, but we do have domestic. Even 28, there are a couple modules are using domestic too. But still, by far, it is the applied, the lens and so on. Okay? So they are not onto 28 nanometer, but they are a player at the 45, 40 nanometer. And they are good players on the 65.
What is CP testing?
Chip packaging. Okay?
Quick question on the equipment side. So already we're seeing a lot of consolidation, even in the international market, on the equipment guys are. So how do these Chinese equipment vendors?
You know, you raised a very good question. I'm not a businessman. First, I don't work for Lamps. I don't work sorry. I don't work for the China domestic tool makers. Okay, and they need to figure out their roadmap. But the ARs, that's not ARs, but we sometimes we get the request, through national funding project and so on. They say, okay, we'll fund your 28 nanometer as a project under some national project, and at the same time they have to test so many domestic tools. Okay. Now, it does in many cases it does provide some benefit to SMIC. I can give you one example in some of the CMP slurry area. On the 45, it's almost entirely domestic. Okay, save a lot of money. Okay. But on the other hand, when I start my team's working on 28, and we start with the domestic, and it's not stable, so we went back to the external. Right. But we're always keeping an eye. But again, we will not have one vendor. It's not one replacing another. It's really that we want to work with both to the advantage of our company. Okay. But we do get some benefit. So we get a lower price, but they are a little bit more trouble, in terms of the reliability and so on. Not too bad, but that's part of the qualification. So they're not too bad. But is it as good as applied? Sometimes no. But it is growing. It is growing. Okay. This is the sort of the applications that our technologies support. Okay, and we can break down into those domains: power management, wireless, wireline communication, image and display, which I told you we are actually a fairly big player, but I think we are going to get bigger. We have a lot of nice technology coming out, okay, including 3D CIS and so on. It's coming out. Okay, so MCU smart card, that's another sort of China unique kind of product segment we need to address, and we are doing that. Connectivity, mobile computing, memory, and we have a lot more than that. But I'll show you a little bit more. Digital home, set box TV, and so on. Okay, so we are addressing, more or less all those markets. This is again showing short time to market. This advantage where you guys are not design houses, you are academia, you are scholars, and so on. And this is the sort of the sales pitch kind of show to our customer. You come to SMIC, you get a one-stop service. Okay, but I didn't take this slide. I apologize. But still, it tells you that we do provide design enablement, mask. We have our own mask shop, and wafer manufacture, of course, wafer probing, wafer bumping, but this is done by Siltech a lot, but Siltech is a part of SMIC. So we actually provide all those services in-house, including mask shop. And we are able to provide adequate mass service to 28 nanometer. Now we're looking at 2014 nanometer. Can we do it? We do have a lot of restrictions from U.S. government and Japan and so on. What kind of little tools and so on. We do have limitations. So our challenge is pretty big. We were able to use older generation to actually meet the modern generation of technology. The assembly and final test, we have a lot of partners, Encore, Spill, Topan, and so on and so forth. Okay? So this covers a range of activities of course, we have marketing, sales, and everything. Okay, last part, strategy. As I said, I had a cartoon. This is a, the TSMC guys are like the big Japanese sumo wrestlers, 335 pounds. And that cartoon had a SMIC, little teenager boy with a pigtail, on the back with a slingshot, okay? And that was my cartoon, but I didn't put it in. So anyway, you get the reason, okay? We are much smaller, okay? We have a relatively short history, about 10, 11 years. And in between, we also have some missteps created by ourselves. Some that are external environment induced, but some of them are self-induced. Okay? But anyway, we came along up and down, but we did grow. We are getting better, but still, the challenge is very large. So the first thing, the new management team came in third quarter of 2011. We had a new chairman, we had a new CEO, who is my boss, Dr. Shiuh-Wuu Lee, T.Y. Chu. And this is a strategy the team implemented. Immediately, I would say this phase is pretty much done. The first one. We'll continue to drive that. But this we reap a lot of benefit. Is that near term, full utilization of existing assets. Sounds simple, but it does take some planning, some analysis. How do you plan your product in which fab? Where you do your manufacturing for certain technology that give you the maximum flexibility, and so on and so forth. So we reached a very high utilization rate in a very short couple quarters after the new team was implemented, and this started the period of profitability. But now we're in the midterm or medium term, and there are two things we must do. Okay, this is high-level statement, but this is something we practice, and this is something that I have been measuring. I, along with many other people, are measuring two things. One is that I'll talk about this first. On the advanced technology, remember you talked about the Chinese leading design houses need advanced technology earlier and earlier. So my mission as to lead in leading the TD team is we don't want the gap between us and the leading company become larger. If at all, can I reduce by a quarter, by 2 quarters? That helps a lot. Don't dream we'll do better than TSMC. That's true. They are very, very good. I have awful lot of respect for TSMC. Okay? However, we cannot let the gap increase. Sounds easy? No. Very difficult. But I think we're doing a decent job. Okay? You'll see my technology woman. The other thing is differentiated technology. One thing people say, why, sort of saying, why are you working on 0.18, 0.13 and so on. I'll give you one story. I already told you about CIS before. We have tremendous business opportunity even on the 0.13, 0.11 with BSI. Customers, 6, 7 customers waiting at the door. Even now. Okay, so the other thing is, I'll give you one example. For example, we I cannot go into detail. We have a lot of patents filed, but by innovating the device structure, the end result is that we can produce at 0.13 micron technology, SRAM. Even some of the logic, but especially SRAM. We can produce at the same density as 90 nanometer. But the cost is the 0.13 micron technology with almost minimal change. Almost no tool needs to be added. Because that's an investment. Then right away you have depreciation and so on. And it was quite a piece of novel, actually quite a novel work. Okay? I think we had something like 20 or 30 patents filed. That's just one example. So we can use our 0.3 to compete at 90. Now my job is looking at can I use, and moving that onto 65, and my 65 can compete with their 40. Now this is for certain application, not for every application. This has to be SRAM, those things dominate the product, and we can really take advantage. And the cost saving is tremendous. So that just gives you one example. There are many examples. And this is AR given by, by the CEO to the TD. Is that create differentiated technology with innovation, whether performance or cost. So we don't just drive advanced technology, but we also get into new things like SOI. But again, it could be on a mature node, but it has very attractive market. In the long term, we must push forward on advanced logic, on advanced technology. In fact, that is not just logic. There are other advanced technologies. So that's long term, and maybe part. And in this differentiated technology, we really believe there are areas we can become number one in the world. On 20 nanometer, well, I have Intel sitting there. As long as Intel is around, for the very, very foreseeable future, I will not have that dream. Okay, they are excellent companies. TSMC is strong, right? I will try to do good, and our technology will be a couple years later, but our technology will be as good as theirs. That we can do. Not easy because we don't know how they did it, but we will have to do with all the constraint I have. It's not easy, but I have confidence. My team is growing at SMIC. Okay, we got a couple of illustrations. But on the differentiated technology, on 65, I can create some ideas that TSMC already moved forward to 20 nanometer, to 20 nanometer, even 40 nanometer. But when I come back, when we have innovation, we will be the best in the world on that technology. And there's still a lot of money to be made, as shown by our example of 0.1. Very novel idea. We can actually make awful lot. Okay? All right. Okay. This slide really shows again the differentiation strategy. This is a logic technology. All those are below this line means all those technologies are in volume manufacturing. 28 nanometer is coming up, and we already started about a year to year and a half on 20 and 14 nanometer. Now, this is characterized. The application is CPU, GPU, and so on, AP, and so on. And the characterization of it is that it's highly competitive, extremely CapEx intensive. Okay? To compete or to maintain certain competitiveness for SMIC, it's extremely difficult, but we're determined to do that. Okay? Now, we leverage this to generate a so-called RF technology. It's very cheap. You need to add some RF elements, the inductors, varactors, and whatever you have, some of the elements. It's not too expensive. And those are the market that we're driven. And the same with embedded non-volatile memory, CIS, PMIC, and others. And here are the applications. And basically they are characterized as market demand are quite large with strong growth, in particular in China, and much less expensive. So we are working on this late as well as this. But this late is focused on what's uniquely growing in China, with focus, with those emphasis on it. Like I mentioned, CIS.
CapEx intensive means CapEx intensive.
CAPEX means I need to build a factory, I need to buy tools. Those are capital investment. Okay? And, okay. This one is showing how we leverage it. And I think earlier there was a question, And we put in a lot of investment here. I think roughly my budget is probably more than half. Okay? And personnel out of the 700 plus R&D team is also about half. Just on those a couple logic technology at the time, right? And so it's a very heavy investment. However, this is not just for the logic technology-based product per se, but also move horizontally. Many of the technologies are leveraging the platform. Try to develop RF we just mentioned. Okay, MEMS. Some of the older technology we're leveraging. So those become very cheap. Some of the reason is because we have the baseline logic. That investment and tools is already in. But we need to buy a few new tools, of course, but not on a wholesale basis. Okay? So that's our strategy. And you can see that all those are available. Those are what we're working on. Flash, like eTalks, we have those technology already, but we're actually working on 3x NAND, as well as 45 nanometer node. And embedded flash, we are working on 55 nanometer, and that's with a major Chinese, very major Chinese consumer house, very major one. EEPROM for the bank card, 0.11, 0.13, as I mentioned. This will get into a revenue stream next year. Okay? Hopefully in the medium way. And image, I already mentioned. Those who are working on 0.11 BSI, that will go into production in Q1 next year. And then followed by 90 nanometer, and then followed by 60. So all those will be one after another coming up. And then even integrate with 3D technology. So MEMS, again, we have here. So you can see that we develop this, leverage this as much as possible, develop some of the value-added technology. And hopefully some area we can, with special innovation, to actually take certain amount of leadership, if possible. Okay, let me talk a little bit about 28. Mark, you can fall asleep for about 1 minute. Yeah, you know about it. So we are, what happened at SMIC. I'm still very proud of my team. We are several years behind TSMC. But as far as a high-K metal gate, we are really, except for TSMC, I think we're very competitive to the other companies. They are having, I think some of them was a decision they made to go gate first, and they're changing, etc. There are other yield issues and so on. And we are marching into that very quickly now. The big challenge, of course, SiGe, embedded SiGe for PMOS, and I think we have that process module. The unit process worked out very well. On patterning, again, we're using a scanner, 40 nanometer based, and to do this 70% pitch shrink compared to 40 nanometer. High-K, gate last, and also our back end, for the first time in several generations now. We were a little bit behind industry. We still use 2.75 K value back end dielectric. Now we also on this technology, we are totally moved on to the 2.55. Okay, so we should be very competitive. But let me stop here for just say a few words. Each technology, some of them are major, some of them are minor. And the industry, all the analysts that we can meet and all the customers we can talk to, the 65 was a major one. Okay. 90 was very minor. That was before, right? 90 very minor. 65 was a major one. In fact, we also had a 55, half no share. That was generating a lot of revenue. 40 is sort of so-so. Better than 90, okay, but not a tremendous explosion compared to 65. Maybe about the same. 28 people saying that this would be a very major no, and very long lasting. So we put a lot of emphasis on this. And I guess some of the help was from other companies because they made a certain decision that was probably end up favorable to us. Some things because I think we probably did a few good things, along with some bad things, but at least we did a few things. I think our schedule is pretty competitive. We still have a good opportunity to get into the 28 nanometer market. And on the 28 nanometer, we developed two technologies, which both will be process freeze will be in 1.5 weeks. And then followed by a quarter and a half of CIP, continuous improvement, we're moving to the back. Okay? One is high-K metal gate loss. The other one is polysilicon. Then once that's done, once that's freeze, around Q1, there will be derivative coming out, multiple derivatives. There will be cost-down version of high-K metal gate. There are some customers very interested in that. Yes, you're going to lose some performance. I won't tell you which performance, then you'll know what was my customer. But anyway, so there'll be a whole derivative, okay, of high-K metal gate alone. Then on the polysilicon, there will be RF. And that RF is not just by adding a few RF elements, but by truly doing an RF high-performance process on 28 LP. Okay?
And these are all bulk silicon technology?
Those are all bulk, yes. SOI on the advanced node, right now, at least it's not officially turned on yet. On some of the mature technology like 0.18, yes, we are moving a big way into RF SOI. And the RF SOI, normally they require a little bit older technology, but very interesting. Don't think that the only thing interesting is the 10 nanometer and maybe for university professors because you gotta have that to get the national funding. But in industry, maybe the TD team needs a little bit of the technical challenge, but the driving force is that will this make money? I'm sorry to say that, but that's a hard fact. Okay? Along the way, we will have some fun. I'm sure.
Quick question.
Yeah.
What are your targets for ultra low K?
2.5.
2.55.
Yeah, already in fact we developed so fast. When we start a program, we have pretty much the ultra low K thing. Maybe we don't have all the reliability data done, but in terms of performance, we did it in about 6 months. Very good. Okay, so I talk a little bit about my team. I think the company, and in fact, I hope there are some students, and then professors too, to help me to recommend students. I've been at I was at the Intel for 20 years, and I think did half decent in my career there. I became a fellow there, and I was leading a very, very high quality team. I had lots of fun. Then I retired and I moved to SMIC. I enjoy every moment, just like I did at Intel. It's a little bit different fun because the team needs a little bit more guidance. The guidance is not necessarily say how do you do implant, how do you do diffusion, all those kind of things. It's methodology, organization, structure, division work within TD, within the company. A lot of those things need to be cleaned up. I think that was a lot of my focus. Certainly drive the team, program review and everything. That's just normal part of team. Okay? I think the team has grown quite a bit at SMIC. Even at the end of 2011, we were about 425. Now we are at the end of 2013, we are over 700. Okay? And we'll continue to grow because we have to. Of course, I have to watch the usage of manpower very carefully. We cannot afford waste. But as you can see later, as you see some of the tree structure, how many technologies we're working on. And there's a lot of support activity. Every one of the technology you need supporting to do design rule, DFM, DRC, LBS, SPICE model, the whole loads of supporting infrastructure we need to provide. So education-wise, we have about 700, but 50% was master degree, about 15%, I believe, yes, with PhD. Okay? I need more people with advanced degree. Okay? If you have a good student, excellent student, I will hire without limit. No headcount limit. Normally I do have a budget. But anytime there's a tremendous student or a tremendous veteran from some company, I will hire on the spot. Okay? So that's for education and the working experience. Most of them have actually 2 to 6 years or 6 years and above. Yeah, this is 2 to 6 years, and this 40% actually greater than 6 years. So the team is maturing. I look at the team and as probably facing a very interesting work as far as in the China region. We are the leading company. We're working on actually some of the very advanced technology, maybe not quite advanced as some of the most leading company, but we're up there, and we'll narrow the gap. Okay, and I look at the team as 3 stages, or the company. First stage, technology license. In other words, go out, buy license, and then transfer. Second stage, joint partner. Third stage, independent. Not that we don't talk to other people and work together. No, we always do that. But essentially, you have the ability to do independent. I think we certainly passed the license, except a few small special cases like SOI. We haven't done it, we might license it. But after a while, we'll start doing independent. Okay? That's a strategy. And even in the logic, most advanced technology, 45 nanometer at the SMIC was a licensed technology. 28, by no means it was licensed. Even though people heard about SMIC and IBM as a JDP. But I can tell you we are very much doing a lot of independent work, probably more than 95%. And so as we move into the 20 nanometer and 14 nanometer, we expect, again, we'll work with some strong company together, but again, mostly we have to rely on ourselves. I think the team is actually moving to that, and there are certain areas totally independent, like the MEMS. We're doing very innovative work on MEMS, on 3D IC, TSP, all those technologies. We're doing actually quite innovative work.
So, Shiuh-Wuu,
Yeah.
I have a question on this, your team.
Yeah.
With the master and PhD.
Yeah.
Where did they receive the education? From
Let me see. All over in China. In fact, I don't remember all the names of the professors, so I don't want to misinform people. But certainly Beijing, Tsinghua, Jiaoda, Fudan, Zhedan. Okay, some well-known, but also like Kejida and so on. And there are a lot of good universities, right?
Mainly from that in China.
Okay, that's part. There's also, roughly speaking, maybe half of them coming from abroad. Like myself. Okay, like I recruited, for example, Shaohong Yu, for example, from TI. Those are PhD from abroad. So I don't have a fine breakdown, but we have all over. And now there'll be a couple more coming from the US and very experienced people. So again, I don't just differentiate where they come from. As long as they are good, smart, whether they are old like me, or I'm too old. I don't want to recruit myself. No, too old, useless. But I do want to, like experienced and young. I think both are important. Okay, we need young people to come in to say no to everything we do. Okay, but we also need experienced people to create stability. Okay, so we need them all. Okay, here very quickly, how am I doing in time? Am I running out of time?
No, it's okay. 15 minutes.
Oh, okay, I'll wrap up. Okay. So very quickly, more than more. People hear this, it's like a commercial, right? But truly, okay, it is a real thing, right? So in the center, between those two lines, those are the logic technology and some of the derivatives. Remember the tree, the PIMIC, the CIS, the RF, mixed signal, non-volatile, etc. Conventional CMOS technology. But we also have specialties, IPP, very, very high performance, high quality, like inductor, for example. It's sealed in a cavity, and so on and so forth. And we're doing this with some US companies. Quite high ASP product. CMOS MEMS and so on. But with all this, you want to build a system, we need to have more innovative packaging or assembly method together. With microbumping, TS4 I/O interconnect, interposal, with wafer level SiP, wide I/O, and this is something that we'll target for probably to support 28 nanometer. Okay? And then 3D IC. Okay, that's eventual goal, truly 3D IC. To achieve that, we actually just formed a CBS 3D. That sounds CBS. That sounds like a pharmacy in the U.S. Okay? I even said CBS. It's CS, Center for. This is wrong. This is Center for Vision. So it is CBS. They type it. Center for Vision, Sensor, and 3D IC. And this is a particular focus on that, doing R&D. In fact, we also have a factory dedicated and run by TD. Okay? Because a lot of those modules are new. And a lot of our fab people are not familiar with it. It's so new. I told TY, let TD run. I'll run. Okay? It's quicker. Okay? So we run a fab. It doesn't do everything. We utilize other fab as well, but we produce the kind of process step that are new, and then we bring to other fab to finish. Okay? And we also, this is something that we like to do some research together with universities. Okay? Our work model hasn't totally formulated, but this is something we like to have joint work. Some center, people can come in, bring ideas, try that out, and so on. This is our vision. This is just announced about 2 months ago. I had a press release, but this is right now the stage is how do we? This center is dedicated to our own internal R&D, and how do we push manufacturing out of the door? Okay? And we anticipate to start ramping the revenue this year. Okay? For MEMS, CIS, together with 3D IC. Okay? But the longer vision is that I would like to see joint research, partnership, some place Philip can come in with a student or some ideas. We see if there's some joint interest, common interest, if it is, we can run some wafer for you and things like that. Okay? Okay, this will be my last slide, and I think I have one more, I won't show it. This is basically saying, again, on the 12-inch platform, you have more advanced equipment, baseline technologies, you have core devices, but however, it's higher R&D cost, higher manufacturing cost. But along each domain, we have those technologies on 12 inches. On the 8-inch platform, similarly, but with the lower R&D cost, greater flexibility, and lower manufacturing cost. We have those technology provided. But through technology such as the TSV, interposer, we can integrate any part of that together onto the system. And what is the advantage? Well, people talk about power, performance, shorter interconnect. You can have a wider line. You put everything on the chip. There are other benefits besides power and performance. Yield. I break up into smaller parts. The yield is less of a problem. Faster to market. Maybe in an SO system, some of the parts I can use 0.13, it's already there. I don't need to redesign. But they are a small part of the whole system I do need to design. It's not the whole way. And also process optimization. If I have a non-volatile memory and if I have logic all on the same embedded, there's the influence on each other. How do I co-optimize? Now I put in MEMS, I put in other things, CIS, wow. The optimization objectives constraint becomes so complex. You probably will not be able to get the absolutely optimum anymore. If we use this, you can really optimize your technology. And then, through the 3D IC or the interposer, you put together a system that is truly optimal. Now, there is certainly a cost. Cost in the design will be less. But the cost of the TSV right now is still quite high. So we need to bring that down. Okay? So I already mentioned pretty much here, boost the manufacturing efficiency and extensive process offering and so on. Okay? There's just another figure, this is sort of representing our roadmap, but now we schedule things like this is how we envision. We might even eventually we have to provide IPD, integrated passive device I mentioned about, MEMS, CIS, logic, non-volatile memory, even LD modes, bipolar, and things like that, but also SOI. Okay? So all this can be built in, and SOI is not even the conventional SOI, we have our own structure. Very novel structure, which again, I cannot talk about it, we're applying lots of patterns. So we are trying to get this thing that we can provide a very complete platform, depends on what customer wants. So you have technology, process technology, you have integrate, I call the word integrate, that to enable the SoC integration. Okay, this is just saying, we have a lot of customers. This is the IP vendor, partners. Bright, that's part of the, I guess partially owned, or actually part of the SMIC, I believe. But we do have a lot of international partners, ARMS, for example, Mental Graphics, Cadence, Synopsys, for example. Okay, so we have partnerships with all over. And this is the design house. This is the Fabulous House, or our product partners. And this is all those international houses. LSI, Qualcomm is probably here, Broadcom is here, Silicon Motion and Copan, all sorts of partners. Okay, and so we are truly a international company. It's not a close eye, only focus on China, but we do have important China partners. Okay. High Silicon being one. There are many others. RDA, very important, and so on. Okay. And this is a list I won't go through. This is a list that we're working with the Chinese tool makers and material suppliers I mentioned. We're truly putting a genuine effort to try to help them to find out what are the problems through real silicon data, real experiment, and possibly give them some advice. And something I've qualified again, but this is not, we don't need to go through detail. But this is a real list we're working with on 40 and also on 28. Okay, this is a PR slide from my HR. So okay, I think that's it. Thank you very much.
Thank you. So now floor is.
Okay. We have 1 minute, 10:30. Mark.
Shiuh-Wuu, so it's mentioned in your bio, you had a very distinguished career in modeling and TCAD at Intel. So I was wondering if you could comment on what your strategy is in terms of utilizing TCAD and whether or not you have much of an internal effort at SMIC.
That's a good question. Certainly my role at SMIC is no longer just TCAD, but TCAD. You're going to talk about TCAD 20 years at Intel, but actually one small comment, it's more than 20 years. It's probably 25 to 26.
Yeah, I'm talking about me.
You're talking about you. So Mark's experience
That's
at
right.
Intel as a TCAD.
Yeah.
Okay, I'll just change the title of your talk. Okay, let me answer this way. I think TCAD, you can use TCAD, you can drive TCAD at least 2 levels. Like Intel, or we did. Okay. I think we built one of the strongest TCAD teams anywhere. But you must have the resource and patience. Okay. And at Intel, we start implementing our own models, physical models, company models, right? Process, device, bench structure, everything. Why? Because we cannot wait for the university. It's necessary to be done. Now the university is behind us. I'm not saying that. University professor focus could be on something else. Okay? For example, I remember in the 90 nanometer we faced poly depletion. That's a device issue. Okay? On the compact models, we don't have BC, we don't have a polar depletion. But can Intel wait for Professor Chen-Ming-Gu to put in a polar depletion before we design our product? Absolutely not. And I told Chen-Ming that. I remember once he visited me at Intel, I said, you don't have polar depletion, I'm going to put it. I cannot wait for you. We're a multi-billion-dollar company. I cannot wait for you, right? That's just one small example. So Intel is even driving the fundamental model development, implementing into its tool, because it is leading. Sometimes you don't have available models or tools. And I was there, and for many years, I was driving many tools that was unavailable in any EDA company. SMIC needs different things. Do we need TCAD? Absolutely. Do I need a combat model? Absolutely. But the needs are different. First of all, on the combat model, I first of all cannot create my own model. TSMC, as a leading foundry, it cannot create its own model because the model has been propagated to all customers unless they have a big service team, support all simulation bugs, everything. No, that's too much for even TSMC. So we use industry standard, right? That's one thing. For process, like TCAD, SMIC do not have the resource to develop fundamental quantum mechanics-based fundamental transfer information. I need my engineer to understand it, apply it correctly. And that alone is not easy. As you know, you were head of the application group for many years. The application is not just push a button, put in a simulation file, boom, I got the answer. No, it's an advanced application. And this is what I push at SMIC. And another aspect, the size of the team, when I went there, was 8 people. Now it's almost 20. I'm continuing to build it. Not because I have a lot of TCAD background. I told you, I don't manage TCAD. I manage the whole TD. But I fully understand the power of simulation. If the simulation, you know the limitation as well as how to use it. That's why we need advanced PhD level even, people to run the application. Not somebody just push a button, create an input file, look at ID curve, I got it. Absolutely. TCAD is not perfect. Okay. Especially as you guys push into the most advanced technology in the unknown domain. You need to know what to do. What's the limitation? Okay. So number one, we don't develop a model. We don't have the resource. But I do need, and I am, and I will continue to build an advanced application team with very high-level skill. And the number is increasing. I think I'm up to about 20. In 2004, I probably add a few more. In fact, the domain is also expanded. We went from process and device. Now I'm into CIS, light simulation. I'm into a chip package. Again, at Intel, I know our colleagues developed the fundamental like iCrack and those kind of tools. I don't do that. I go to vendor. I go to some of the vendors and say, hey, do you have such a tool? Okay? And give me training. Send your expert. I want a deep training, not just a commercialized training. And we start applying. It's very powerful. So you're in the right field. You will always have a good job.
Will you hire me on the spot?
Mark, anytime you want to come to SMIC, just give me a call.
Okay,
You're welcome to stop.
So it's time for the coffee break. Let's thank Dr. Lee again. So we will resume the next session 10:50.